Hope you guys are doing well. We're going to continue discussing linear regression, which we were working on last time. And last time, what we did is we derived an equation for the least squares coefficients that used this A matrix here, which has our feature data, as well as a column of ones. And here we have our targets in a vector y. And this was the expression that we derived, and this expression minimized the, it minimized this RSS, which is the sum squared difference between the true targets and our predictions. So we derived that particular expression for the RSS minimizing coefficients. And the issue with this is that that expression is not very insightful because it's this complicated function of all these matrices and so on. So we're going to try to make a bit more sense of it. So in order to do that, we said we're going to start by pulling out the intercept coefficient, beta 0, and collecting these slope coefficients, beta 1 through beta d, into this vector, which we call beta, and then in the subscript 1 through d. And then we went through a quick review of some basic sample statistics, like the sample mean, which is just the arithmetic average of a list of numbers. So we have the sample mean, for example, of the targets y. We're always going to refer to that with a bar. Sample variance, which is the average squared deviation between y and its mean. And then we have the sample covariance, which looks at the relationship between the features and the targets. At least this one is looking at the jth feature and the targets. So these are all scalar statistics. Notice the small, or the non-capitalized letters. But we're really dealing with multiple features. So we actually will need to consider the sample mean vector. So these are our features for the ith training example. Here we're having the average over our different training examples. We get x bar the vector. If you look inside, you'll see the sample means for each of the features individually. We also have an extension of the variance to the autocovariance matrix. So here we have, as a column vector, the deviation between xi and its sample mean, and then here as a row vector, the same thing. And when you look at the average of that, because this is an outer product, you get a full matrix. And so this full matrix is called the autocovariance matrix, sample autocovariance matrix. When you look along the diagonals of it, you see the variances of the different features. And when you look at the off diagonals, you see the relationships between the different features. And finally, we have the sample cross covariance vector, which looks at the relationship between the features and the targets. And this is a vector quantity here. So those are the statistics we need. And then we said sometimes when you're doing derivations, there's a slightly different form of the statistics that's more useful. So here we have the original definition of the sample covariance matrix, but here's an alternate expression that does the averaging directly over the xi quantities and later subtracts the outer product of the means. That's different from what we're doing here. And there's a similar one for the cross covariance. Here we're doing the average over the I quantities alone without the means and subtracting the means later. So over here, looks like I forgot, there's an underline because x is a vector. Okay, so that's sort of the setup, and then we just started with the derivation at the end of the last lecture period. So what we need to do is we need to, find the RSS minimizing values of all our coefficients. And so let's start with coefficient beta 0. So the way we're going to do this over and over in this class is we're going to try to find the beta vector that sets the partial derivatives to 0. So one of the partial derivatives we'll be working with is the partial derivative with respect to beta 0. And then the other partial derivatives we'll be working with are the partial derivatives with respect to all the other betas. But because beta 0 works in a somewhat different way, we're going to treat it separately. Okay, so let's do our derivation for this. We're going to do partial derivative of, here is the RSS. This is yi hat. And we said that when we do partial derivatives like this, the first thing to remember is that because differentiation is linear, we can sort of move the derivative through the sum. And then we are faced with doing the derivative of this quadratic. For that, we use the chain rule. So we get 2 times the interior times the partial derivative of the interior with respect to beta 0. And when we look at this interior, the only thing that depends on beta 0 is this term. And so that partial derivative is easy, that's just minus 1. And so here's that minus 1 term. Here's the 2 that came from this, and here's the interior. So that is, this is basically one equation that our beta vector will need to solve. But there's a few more equations that we can get here. So before I move on, are there any questions on anything we've done so far? Is everybody good? Okay. So let's move on to doing the partial derivative with respect to beta j. So, so here we have, basically this is just the same expression as above, but now beta j, this is going to be one of the j's between 1 and d. That beta j is actually inside here. So to get access to that, let's expand that into a summation. And we're going to write that summation not in terms of the dummy variable j, because j is something we fixed over here. We can't use j again. Let's use j prime. Okay, so now we're ready to do our partial derivative. So again, we move this through the sum. That means we're going to have the sum over here. Sum over I equals 1 to n. And then we take the partial derivative of this using chain rule. That's going to be 2 times the interior. So 2 times the interior, and let me see how I'm writing that. Okay, we're going to have yi minus beta 0 minus xi transpose beta 1 through d. And actually, I meant to leave a little bit of space in front of it. Let me move that a little bit to the right. And actually, for the next step, I'm actually going to move this 2 to the outside. Sorry about that. Okay, so the last step for the partial derivative is to do partial derivative with respect to the interior here, or maybe here. So how do we do that? Let me ask, is Wyatt Judson here?
That's me.
All right. So yeah, so let's do partial derivative of this with respect to beta j. So do you see what that's going to be?
Yeah, with respect to beta j, would it just be then xi transpose? Xi transpose?
So okay, so this is all a scalar. Right, this is just a scalar quantity. So this is a scalar. So there's no vectors involved. So just focus on the part that I underlined. So there's no vectors there at all, right? So this part here is not a function of beta j, right? So we take the partial derivative, that goes away. This goes away because j is not 0. So really, we're just looking at the partial derivative of this. And so again, because of linearity, I can move this partial derivative through that sum, and then I can apply it to this, right? So now there's basically going to be 2 cases. Either j prime is equal to j, or j prime is not equal to j. If j prime is not equal to j, the derivative vanishes. But if j prime is equal to j, then the derivative of this respect to beta j is?
It would just be 1.
1. But then we also have this term here, which is going to be xij, right?
Okay.
Not j prime, but j. So that's the final answer. Oh, and there's actually a minus because of this. So that goes over here. Okay, is everybody good with how we did that derivation? Question?
I don't get it, like, originally, xi transpose is like a row.
Yes, exactly. Let's draw it out. So that's a row vector, and beta 1 through d is a column vector. And when we do that, that's called an inner product, we get a scalar. So like this whole thing is a scalar, right?
Xij is a matrix, right?
No. So this xi transpose is a row vector, and that has scalar elements in it. And the elements inside are these guys. It's xij prime, where j prime goes from 1 to d.
Okay.
Does that make sense?
That's a,
Yeah.
so it's a scalar, so xij.
Yes, right. So, and you can also see that it's a scalar because it's not bolded. So if this was a vector, I would have made it bold. If this was a vector, I would have made it bold. So that's part of my reason for using bold for vectors and matrices is so that it's easy to understand what's happening here, right? So when you look at this, you say, oh, that must be a scalar, that must be a scalar. Yeah. Okay. Any other questions? Okay, great. So yeah, so this is the expression we have. And so basically, this gives us some systems of equations. We have one equation here, and we have d more equations here, and we have a total of d plus 1 unknowns. So it makes sense that maybe we can figure out the optimal betas, all d plus 1 of them, by solving this system of equations. So essentially, we're going to do that, but we're going to just do it step by step. So so let's first try to make these quantities a little bit more familiar by getting rid of things like the 2 and the negative, and we're used to seeing those statistical quantities that we derived earlier with averages, so that would mean there's a 1 over n, and we're missing the 1 over n here and here. So because we have equals 0 on the left side, we can just multiply both sides of those equations by minus 1 over 2n. And that won't change the left side, but it will get rid of the minus, get rid of the 2, and put a 1 over n there. And then what remains will start to look like the statistics we're used to seeing. So that's our approach. So we're starting with this equation, multiplying both sides of the equation by minus 1 over 2n, and that gives us this, where we have this 1 over n here. And then we can expand out this sum. So we have a sum, or an average over the yi's. That's something we've seen before, right? That's y bar. And then we have an average of this constant. What is that if I have that quantity? 1 over n, sum I equals 1 to n of beta 0. So what was? So there's no, beta 0 is a fixed number, right? So there's no mean associated with it. It's just beta naught, exactly. I'm saying this because this, I realize this has confused a lot of students in the past, like what this means. So one way to think about this is the following. Because beta naught is not a function of I, you can actually move it out of the sum if you want. And if we did move it out of the sum, we would have to leave the value 1 behind in the sum. Right? If I divide out by beta naught, I have a 1. And now when you look at this quantity in the square brackets, that should be more straightforward. What I'm doing is okay, one way to look at it is I'm taking the average of this fixed quantity 1. Another way to look at it is I'm summing the value 1 n times. 1 plus 1 plus 1, so on, n times, and I'm dividing by n. That gives me 1. So there's many ways to look at this, but at the end of the day, this is just beta naught. If you average a fixed quantity that doesn't change, you just get that quantity. Okay, so for that reason, when we average this beta naught, we just get beta naught. The average goes away. Any questions on that, or is that clear? Okay, good. And then the last thing is we have the average of this quantity over here. And on the right side, you can see that this is not a function of I. So that means we can sort of conceptually just think about this as a unit and you know, evaluate that. And that's just the average of these xi transpose vectors, which is just the average vector transposed. Okay, so all in all, we get this equation, which says, in fact, let's just move beta naught to the left side. We then get beta naught equals y bar minus x bar transpose times the beta vector sub 1 through d. Yeah. So this says if you happen to know this beta vector, then since you know these other quantities, you also know beta naught. We don't know the beta vector yet. That's something we need to figure out next. All right. All right, so any questions on anything on this page? Yes?
So beta naught is an independent variable, we don't know.
Yeah, so if you remember, beta naught is our intercept term. If you remember our regression plane, it's the thing that slides, it's how much we slide it up and down. And then the beta 1 through d contains all the slope parameters which describe how we tilt the plane. And so we're just kind of separating them out. And so we see that the optimal height of the plane can be computed from the mean of the targets and the mean of the features and the slope coefficients. If we knew the slope coefficients. We don't know them yet, but that's our next task. All right. Any other questions? Okay, great. Let's move on to the next step. It's kind of similar in spirit. I filled in some of the blanks here, but let's take a look. So this is the other equation that we derived. So this is our other equation here. And we're going to do the same thing. We're going to multiply both sides of this equation by minus 1 over 2n. And what that's going to do is it's going to give us this form, which has this nice averaging operation. And then we can sort of distribute the terms here, and we get the average of this. And the second term here, you can see that the averaging doesn't affect beta naught, but the averaging does affect this. And so if I average this over the i's, I have x bar j, which is the mean of the jth feature when I look at all my training samples. And then finally we have this last term, which involves the average of this product of xij and xi transpose. The first is a scalar, the second is a row vector. And then over here we have our coefficients. And so this is an equation that we would like to solve. It's actually going to be, for every j, we have a new equation because we have this j dependence. Okay, so the first thing we'll do is we'll plug in this equation here, beta 0. We'll plug that into here. And after we do that, the y bar up here manifests over here, and this other stuff shows up over here. And now we're getting closer. Here's a little trick we can do. So xij, we can think of that as the jth component of the xi vector. This xi vector, if you remember, it has elements xij, where j goes from 1 to d. So this is just the jth component. So notice that I'm putting these square brackets around everything and looking at the jth term. So I'm basically like saying if I take this and this is a vector. If I extract the jth component of that vector, I will get this. And we're doing exactly the same thing here, but for the mean vector. The jth component of the mean vector is this. And the jth component of the mean vector is this again. And finally, the jth component of xi is xij. Okay, so we've kind of gone from world of scalars to vectors, but this is an equality because we're extracting a j. And the last thing we can do is we can take a look at these quantities and see if we can notice anything familiar. Let's look at that, and let's look at this. So do you remember these expressions that we derived a couple pages back? Let's look at this one. SXY was this average of the xi, yi's minus the means. So here I have the average of the xi, yi's minus the means, right? So this is that S vector SXY. And on the right, we're exploiting this covariance matrix equals this. So it's the average of the xi pairs minus the x bar pair here, and we have average of the xi pairs, xi pairs minus x bar pair, except that both are multiplied by b, beta 1 through d. So basically this gives us minus sxx, that matrix, times the beta 1 through d vector. Okay, so what I'm basically saying is, inside the square brackets, there's a really nice, elegant expression. It's just this vector minus this matrix vector product. And now you extract the jth quantity, and you want that to be 0. But the thing is, we want that this equation holds for all j. So if it holds for all j, that means that this thing must equal the 0 vector. And finally, we can do one final rearrangement to extract beta 1 through d. Let me ask, is G1 tau here? Yeah. So how would we get from this equation, how would we get beta 1 through d?
It should be the S transpose.
Inverse, exactly. Inverse.
SXY.
Yes. Right. That's right. So what we did is we moved this to the other side, and then we multiplied both sides by SXX inverse, which removed the component from this term, giving us beta 1 through d, but then it appended that or prepended that onto that term. Let's add a caveat. This is if SXX inverse exists. So when you have lots of data samples, this thing should exist, but you can get it into a situation where if you have fewer data samples than features, then that covariance matrix will not be invertible, and you'll be in trouble. And in that case, we're going to have to use some other tricks that we'll learn in a later unit, and you'll actually see an example of this in a later lab where there's way more features than there are examples. But most machine learning problems have way more examples than features. So that's the usual case. So this is our expression for the optimal RSS minimizing slope coefficients. And here we're putting them together. So if I stack the intercept on top of the slope coefficients to get the full least squares beta vector, I can also stack this vector below this scalar quantity just to get sort of a concise expression for this. Okay. So this is the least square solution. Any questions on any derivations we did over here? Everybody good with that? Okay. All right, so let's think about a simple case, and it's actually called simple linear regression. And that is the case where there's only one feature. So in that case, a lot of things simplify because this beta 1 through d is no longer a vector. It just has one coefficient in it, which is beta 1, if d was 1. And also this covariance matrix is no longer a matrix, it's just a scalar. And all it has in it is the variance. There's basically two ways to write the variance. You can write it sx squared or you can write it sxx. In either case, That's just the variance of the single feature that we're working with if d equals 1. And then this SXY vector also becomes just a scalar because there's only one feature and one target. So in this case, if you plug in SXX into here, the matrix inverse just turns into a scalar division. So we can do it like so we're going to have y bar minus x bar times sxy divided by sxx, and then we have sxy divided by sxx. So obviously much simpler in the case that you have just a single feature. Okay, any questions on this? All right, and one last thing. There's a special case where the intercept goes to 0. Let's take a look at what that is. So let's look at this case first. So one way that this quantity can go to 0 is if the targets are 0 mean and the feature is 0 mean. In that case, you have 0 minus 0 is 0. So one way that that happens is actually quite common, is that when you get your data, it's a common thing to do as a first pre-processing step to just remove the mean from all the targets and remove the mean from each feature. There's reasons to do that we'll talk about later in the course. It doesn't actually affect the performance at all of this method, but it is something that someone might do, or the data might already have the means removed when you get them. So in that case, you would notice that your intercept coefficient is exactly 0. So it's not a coincidence. It's kind of like it's a sign that someone removed the feature and target means. And the same thing happens over here. If the target mean goes to 0, and if each of your features are 0 mean, then you get 0 intercept coefficient. So that's something to keep in mind. All right, any questions? Great. So now let's talk about how well this least squares fit. How can we judge whether it was a good fit or a bad fit? So there's sort of the standard way of doing this, which I'm going to teach you here. So, and the main idea is we want to use a normalized version of RSS. The reason why RSS on its own is not very convenient is if you take a look at the expression, one thing you notice is that the more data samples n that you have, the larger this quantity becomes. So if someone says you have a large RSS, you don't really know if it's because you have a bad fit or you just have tons of data. So one thing we could do is we could just say, well, instead of working with RSS directly, let's just divide it by n, and that way we remove the dependence on the size of the data set. Just like, maybe that's a more useful quantity. But even so, you would notice for this normalized one that as the values of the targets get larger, like if the targets double, then your RSS would actually quadruple because of the square. Right, so now this thing is still dependent on the variance, you could say, of your targets. And so what you can do for that is you can divide the RSS both by n and by the variance of the targets. And that is a useful feature because it's normalized in such a way that it doesn't care how many targets you have, nor does it care like the absolute size or the statistical size of your targets. So that would be fine to use that, but it's not what's typically done. What's typically done is a small variation of that called r squared, and r squared is 1 minus that quantity above. R squared is officially called the coefficient of determination, and there's a whole explanation for what that means and why that's useful. I'm not going to get into that. If you guys want to take a look at it, you can click on that green link here, and the wiki page is really great for this. But we're just going to think about r squared as like a shifted normalized RSS, and what's important here is to really understand the meaning of a given r squared. So let's first think, what's the smallest possible RSS that we can get when fitting data? What's the smallest value? Yeah. 0, right. That's if we get a perfect fit to every training sample, right? That's the smallest we can get. And notice the negative sign here. So if RSS is 0 is the smallest, then the biggest value of R squared we could ever get is 1, because then this term goes away. Okay, so R equals 1 basically means perfect prediction. So that's the best case. It probably doesn't really happen ever, but that would be what R equals 1 would mean. Now, there's another sort of important value when R squared is 0. The interpretation of that is, imagine that I want to do a prediction, but I'm going to completely ignore all my X features. So it's kind of silly. It's like I'm supposed to be predicting Y from X, but instead I'm just going to throw away my X's and see how well I could do. So in that case, the smartest thing I could do if I'm not using any X's to minimize RSS would be what? Does someone see? Just from the Y's alone, how should I choose this value to minimize this expression? Does anybody see that? Yeah. The mean, exactly. The best thing to do if you're going to ignore your features is just set all the Y hat I's to the mean. So that's what we have over here. And in that case, what is going to be the value of RSS? We've seen this. If I put the 1 over n there, and this is Y mean, you should recognize that expression. This is exactly, that's the variance. So this here is going to be n times the variance if you do that. And so if RSS is n times the variance, so we have n s squared y, you can see the s squared y's cancel, the n's cancel, and you just get 1 minus 1 is 0. So that is basically a predictor where the features are somehow useless. Like maybe somebody generated, completely useless features, no good for prediction. R squared equals 0 describes, what you would expect to see. Or like if you just decide to ignore those features and just choose this as the mean, that's R squared equals 0. So for anytime you do least squares regression on the training data, you will see an R squares somewhere between 0 and 1. It's usually not going to be exactly 0, because even if you generate random features, there's going to be some like tiny statistical correlation just randomly with the not statistical correlation, but you're going to get an R squared which is slightly larger than the variance, and so your R squared will be slightly positive, but it's going to be some number between these. Now, if you ever find that you are getting on some data set R squared less than 0, it's because the prediction was worse than trivial. The one way that this can happen is somehow there's a mistake in your code. Okay, that's one way that can happen. Another way this can happen is you train on one data set and you apply that to a different data set, and the mismatch in the data sets causes that initial solution to be really bad for the other data set. So that's another way you can get negative R squared. But if you do least squares regression and you do it without any mistakes, your R squared is guaranteed to be somewhere between 0 and 1. Okay. All right, so that's R squared. Any questions on R squared? Okay, excellent. So let's just briefly talk about how we compute the least squares solution. So there's a couple options to us. One of the most direct things you could imagine doing is just say, well, we derived this, let's just program this somehow. And you can program this in Python using the NumPy library. And so what you would do is you would first get your feature matrix out of Pandas, and then you would add a column of 1s to the left of it. To do that, you could make a column of 1s, and you could use this horizontal stack command to put the 1s to the left of X, and you get your A. And then you could do this A transpose A inverse. So here we have NumPy linear algebra inverse, and here in NumPy dot T is the transpose, and this ampersand is matrix multiply. If you put a star there, which is what you would do in MATLAB, it wouldn't be a matrix multiply, it would be like a element-wise multiply. So for matrix multiply, we need that ampersand, or at sign, I guess, not ampersand, the at sign. And so that would give us A transpose A inverse. And then finally, we could, there's a couple things you can, so we have our A transpose Y for this, and we could use another at sign here if we wanted for matrix multiply, or you can also use this dot operator. That also works. The dot operator works if you want to do something like X transpose Y. You could do that as X dot Y. Or this even works if it's a matrix. X, Y would be like capital X dot Y. So matrix vector or vector inner products you can do with the dot command. So this is just one way to compute the beta coefficients. So that works, but it's not very efficient numerically, especially as this matrix gets large. And a more efficient way to do this, if you want to use NumPy, is to directly ask it to solve a least squares problem like this. And for that, it has this, this library, least squares, where you give it the matrix and you give it the vector. And that has some very efficient algorithms in it that are going to be more, better than this in terms of speed, but also in terms of precision, numerical robustness. This actually gives you out beta, but it also gives you out some other things, maybe like the tolerance and so on. And so to get out beta, this is the first element of out that you want. And in Python, it always starts counting with 0, unlike MATLAB, which starts counting with 1. So if you want the first of a list of things, you would do basically square bracket 0. Give me the first one. So that's another way to do this. Any question on these routines? Okay, so these are two ways to do it, but there's an even nicer way, which is going to play better with a lot of other things we're going to do this term, which is to use the scikit-learn library. This is like the basic machine learning library in Python. So scikit-learn has a library of commands for various kinds of linear modeling, and one of them is exactly what we're doing now, which is linear regression. And so what you do is if you call this command here, what it does is it instantiates an object. Basically, it sort of makes this object, which we're calling regression, REGR. And this object, this is the object-oriented world here. This is, you could say, a container that has a bunch of stuff in it. It has functions in it. It has places to store data. It has a lot of stuff in it. And for example, if you want to compute the beta coefficients in least squares, you call the fit function. You do that doing regression.fit, and then you give it the features and the targets. It runs essentially something like this internally, and it stores beta internally. It does not report it to you here, but it stores it. If you want to access it, you can. It's regression.coefficients. But right now, we don't actually necessarily need to access the betas. They're just stored internally. Maybe what we're more interested in doing is using them for prediction. So what we're doing in this command is we're doing our X matrix times our beta least squares vector. And as we know, this should give us our predicted targets y hat, and that's what's done over here. So it basically looks inside at the betas that were computed, and then it applies this matrix multiply and gives you this y prediction. So that's what's happening in that step. And then we can also compute RSS. Here we're just looking at the difference between the y predicted vector and the original y vector from our training data. We are squaring every element and summing across the vector to get our RSS. And from there we can compute our R squared by dividing by the number of samples and the standard deviation squared of the variance, sample variance. And finally, there's a lot of different ways to print in Python. This is one way of doing it, but we find that we get an R squared of 0.51. So what does that mean to us again, that value 0.51? Is that Do we have like a really great prediction or a really bad?
It's an okay prediction.
It's in the middle, right? We said it's somewhere between 0 and 1 always, so if it's around 0.5, it's just medium. It's like okay prediction. Okay, any other questions with what we did on this page? Okay, this generic approach, we'll see that we can use this for many other things beyond regression, like classification. And this is sort of the way that scikit-learn works with instantiating these objects, accessing functions in them, like fitting a model, and then doing prediction. This is very, very standard stuff we'll see again and again. Okay, so let's now do a simple experiment just to gain some intuition. Let's look at the difference between simple linear regression, where we have a single feature, and multiple linear regression, where we can use more than one feature. So in this case, as you can see, we just have a single feature over here. We have all our features. So what do you guys think? Is multiple linear regression always going to be better than simple linear regression? How many people think multiple linear regression will always be better or at least as good as simple linear regression? Okay. And how many people think sometimes simple linear regression could be better than multiple? Okay. So both of you guys are right, because I did not really say exactly what I meant by a good prediction. It turns out that if we measure the quality of prediction by only what happens on the training data itself, multiple linear prediction or multiple linear regression is unbeatable, because this sort of covers every case of simple linear regression in the sense that if it's optimal to have, beta 1 non-zero, but beta 2 equals 0 and beta 3 equals 0, that is definitely a solution that can be found by this technique. But if there's a better solution, this will be able to make non-zero coefficients, and this one will not. Now, the way in which this can actually be worse than this is that when you measure performance not by what happens on the training set, but by what happens on some other set different from the training that you try later, it turns out that when you have a bunch of features that act kind of like noise or a distraction, you can actually learn some pretty bad values of beta that are not going to help you on new data different from the training set. So in that case, you're going to actually want to be very careful about which of the betas or which of the features you include for training and which you throw out. And we're going to learn all kinds of techniques to do that in Unit 4. But that's, so, you guys were all right in a certain way with your answers. So let's just take a look at, I made some changes since last semester, and I think this should be the automobile demo, not the diabetes demo. But let's look at the results. They're more important. So what we have here is we have a data set with 10 different coefficients. And what we did is we tried to use each one on its own to do prediction. And so in this case, we're using the first feature to do prediction. And in that case, this was our intercept coefficient, and this was our slope coefficient, and this was our R-squared. If I use the next feature, j equals 1, this was my R-squared, and so on. Let's take a look at these R-squared values. You can see that some of them are tiny, 0.00184. What does that mean? When you see an R-squared that small, what does that mean about that feature? Yeah.
Wow, that's like not very accurate.
That it's not very useful in predicting the target. It's basically, it's not really correlated much with that target. So from the prediction standpoint, it's pretty useful, because this is the least squares prediction. It's the best you can do with that feature, but it's still pretty bad. Now, some of these other ones are better. You can see there's one with like 0.34, 0.32, but the important point is that none of them get up to 0.51. 0.51 is what you get when you use all of them together. when you use individual ones, you can get okay prediction for some of them, but you can't get this good. Because really, when you're using all these features together, you can exploit, you can kind of use, each one of these features could have some slightly different independent knowledge of the target, or, and if you get rid of some of them, you might be missing something on that target. So that's some of the intuition about why if all you care about is minimizing the training error, why it's best to use all of them. Okay, any questions on this? All right. So as I mentioned before, the way that this could, that it could be actually optimal to use not all of the features is if you have a different data set that you're interested in performing well on. And so this slide kind of goes into how maybe we don't just have a training data set, but we have another data set which we'll call the testing data set. And so for this particular data set, what we did is we took the first 300 samples and we used that as the training data. And then we took the remaining 142 samples, we used that as the test data, and we did the least squares prediction on the training data. So notice that we're using the training data here for fitting. But then when we apply them, we can apply those fitted coefficients first to the training and second to the test. And when we look at the R-squares, we see that they're pretty similar, but they're not exactly the same. And what tends to happen is that because your predictors, your beta was optimized for the training, it's going to do better on the training than on this other data set that it was not optimized for. So it's doing a little bit worse on the test. But you can see it's pretty close, which suggests that those two different data sets are statistically pretty similar. Okay, so we'll talk about more of this test and training in the next unit. Any questions? Yes.
So in a case like this, if the R-square value is higher than another calculation that you do, does that mean that the prediction that was made for the higher R-square value would always be a better predictor?
So the predictor is what you have, right? That's a set of beta coefficients. As you apply it to different data sets, you'll get different R-squareds, right? So in this case, we're seeing that when I applied that beta vector to the training, it gave a slightly higher R-squared than the test. It's not impossible that the test is higher. Like, that could happen. That means like somehow that test, those are like easier samples to predict than the training. That can certainly happen. It's probably not the common thing if you randomly separate them. If you take one big data and you randomly separate it into two, it's probably not common that that the test one will be easier than the training enough to make that difference, but it's possible. Yes.
What do you mean when you say easier to predict?
Well, let me give you an example. So if we come back to our picture, sorry, here we go. Some of these points are close to the regression plane, right? Some of them are kind of like outliers with respect to the rest of the data. So when we learn what's a kind of good average predictor, some of these points are kind of hard. Whereas some other points are easier. So it's possible that when I split up this data set that somehow these guys all went into one of them. That set's going to have a worse R-squared, lower R-squared.
So distance from plane defines how hard it is?
At least for linear regression, yeah. Because remember, R-squared is literally just, it's like a normalized version of the squared distance. Yes?
So when you choose the training data and test data, for training data, you choose the first 100 samples.
Yes.
Is it common practice also randomly, take the samples that the test on and then also using the remaining test as the training data?
Yeah, we're going to discuss this a lot more. So typically what we do is if you're given one data set and you want to split it into two, where you train on one and you use another for sort of testing your model, you want to randomize that split. You want to shuffle them and then split them. And so here, it's not clear, we're not doing any shuffling at this moment. It could be that earlier in the code, we did the shuffling already. I don't remember, but yeah. If you don't do the shuffling, you can get into real trouble because sometimes the data set, for whatever reason, is organized in a certain way. Maybe it was like the targets were sorted from small to big. And then if you just take the first 300, you're going to be training on targets with a small value, and then the later ones on a large value. And if you train for one and test for the other, there's going to be a big mismatch. So yeah, there's all those issues. But we're going to get into more of those details in the next unit. Okay, great. Okay, any other questions? All right. So let's briefly talk about one important extension, which happens when some of our features are not typical numerical values. And what I mean by that is we call them categorical variables. So an example of categories, like in this automobile data set, could be brands of cars. So maybe I'm talking about Ford, Honda, BMW. So let's say I have a data set where some of the samples correspond to Ford, some Honda, some BMWs. The question is, how do I deal with that numerically? I have to translate them to numbers, right? Because all of what we did so far is just like processing on numbers. And so the question could be like, well, can I just assign them like integers like 1, 2, 3? What do you think? Is that going to work well? If I, like in my data set, wherever I see a Ford, I replace that with a 1, Honda 2, BMW 3. And then I do my prediction of miles per gallon. What do you think? Is that going to be good, or if not, why not?
No, I think you're imposing like an order.
Exactly. Yeah. Because there is an order to the numbers 1, 2, 3, right? 1 is less than 2, 2 is less than 3. But that particular order might not really be the valid order if there even is an order for Ford, Honda, BMW for the prediction task at hand. Maybe you could say like according to cost or something, maybe this is a valid ordering, but maybe that's not really important for predicting miles per gallon. So what we do when we see categorical variables is you want to come up with a numerical representation that treats them all equally, sort of fairly. And the main way to do that is something called one-hot coding. And you represent each of these brands using what's called a one-hot vector. A one-hot vector is a vector of zeros with a 1 somewhere in it. And so in this case, if we have 3 categories, what we could do the following. We could expand this feature, which we would usually call, let's say, X2. X2 is the brand. We expand X2 into actually 3 variables, and I will denote them with superscripts, X2, 1, 2, and 3. And for any time we have a Ford sample, we will assign those 3 new features 1, 0, 0. Anytime we have a Honda, we'll assign them 0, 1, 0, and BMW 0, 0, 1. Okay. So it's like we're taking that original scalar feature X2, we're expanding it into 3 features, and then depending on the brand, we're coding them in this way. Is that clear what we're doing? How we're doing it? Okay. Now let me explain what happens when we do this. It's pretty intuitive. So this is going to be our new linear model. So here's our new 3 features. And notice that we're going to allow a different slope coefficient for each of them. So imagine now that I look at all the samples that are the Ford samples. For the Ford samples, because of this coding, I know that X2, 1 will be 1. I know that this will be 0 and this will be 0. So all the Ford samples will basically look like this. Meanwhile, all the Honda samples will be 0, 1, 0. So all the Honda samples will basically, these vanish and you just have a beta 3 like this. And likewise, the BMW samples will look like this. So when you step back and you look at this is essentially what we're working with now. You can see that beta 1 is still going to be the slope variable that is used to fit, x1 to y. But essentially, there's now an intercept term for y that is essentially beta 0 plus beta 2. That's the intercept. And for Hondas, the intercept term is beta 3 plus beta 0. And for BMWs, the intercept is beta 4 plus beta 0. So what happens is, it's like we're allowing a different intercept for each category, but the same slope coefficient. Okay. So that's what this one-hot coding scheme does. And that may be a valid thing to do, or you might say, no, I actually think that all those brands should have the same intercept. Maybe what should actually change is each brand should have a different slope coefficient. If we want to do that, there is a variation of that we can do, one-hot coding the slope. It's similar in that we have this same coding, but what we're going to do with it is slightly different. Notice that over here we have the x1 variable inserted in there. And so using the same logic as before, if you say what happens for the Ford samples have 1, 0, 0, so they all look like this. Then the Honda samples have 0, 1, 0, so they look like this. And then the BMW samples look like this. And so now you see that these models, they have the same intercept coefficient, but they get a slope coefficient that differs for the different categories. And this might make sense if you say like, okay, each of these brands, so remember in this example, X1 is horsepower. You might say like, each brand has their own way of measuring horsepower. Maybe they use, something different about how they do it. And so maybe you think like, yeah, BMW's horsepower is always inflated and Ford's is always like a little bit lower. And so what I really should do is I should allow actually a different intercept coefficient for each brand, but I want to use, a different slope coefficient, but the same intercept coefficient. So this is just another way that you could use one-hot coding. Okay. Any questions on this? All right. Gone a little bit over time, so we'll get back to this next time, but see you guys on Friday.